In this problem, I have two bodies. I have the box and the ball, and they're connected by this rope or the string, whatever's connecting between them. So that force is going to connect these two bodies together. In order to solve the problem, I'll need to draw two free body diagrams, knowing that the tension in that string or that rope is what's going to connect my sets of equations. So let's start with the box. Now, one of the things I want to do right here is I'm going to label these just because they're both boxes and balls. So normally I put subscripts like B and B, but that wouldn't make sense. So I'm going to call the box A, and I'm going to call the ball B, just so I can keep them kind of separate, which one's which. All right, and you'll see why I'm going to do that in just a minute. So let's start with the summations. I'll do the free body diagram. This is going to be for A. And for A, it's sitting on a surface, so it'll have a normal force that's 90 degrees to the surface, or what we call a normal to the surface. The rope is going to be pulling from right to left, so that means that friction is going to be going the opposite direction. So there's friction right there, friction opposing the motion. And then I'm going to have the rope pulling this way with tension. It's also going to be accelerating in that direction, so that's going to be the net force. And I'm just going to write the net force as M, let's see, I'm going to write it as M subscript A, the mass of A, times the acceleration. And the Earth is going to pull downwards, since it's not accelerating in the up and down direction, just same length arrow here. Mass of A times G. Now I need to do the ball, B. So the free body diagram for the ball, it's labeled as B. I'll draw it right here. I'll have tension going up. So there's tension. It's accelerating down. So there's mg right there. And I'll call it M subscript B times G. And this is the same tension. Let's say I do have a net force going down. That's the mass of object B times the acceleration. So there we go. There's our free body diagram. It's all set. Now what I need to do is sum up the forces in the x and y direction. So I will start with the diagram A. So for A, I'm going to sum up the forces in the x direction, and that's equal to, well, it's changing speed in the x direction, and the acceleration reassigns the positive direction. So that's going to be m subscript A times A, and that's going to equal, well, the net acceleration reassigns the positive direction. And what that means is that now the positive direction is going from right to left. Tension goes the same direction from right to left, so that's also positive. Friction goes the opposite direction, so I'll subtract it. And then I'll sum up the forces in the y direction. In the y direction, it's not changing speed, so that's equal to 0. And so I'll just make it all the forces going up minus all the forces going down. And I need to change that to m subscript A times G. All right, next. Now remember when I'm doing all the, let's see, let's go ahead and just do the work. The next thing I'm going to do is I'm going to sum up the forces for item B. So this is all for A. I'll put a little A over here to keep them straight. That's A and that's A. And this one's going to be for B. All right. So I'm going to sum up the forces in the y direction. In the y direction, it is changing speed. There is a net force acting on it. So that's going to be m, and it's object B times acceleration. So it's not equal to 0, but m subscript B times A. And that's going to equal, well, the net force and the net acceleration resets the direction of what's positive. So in this case, positive is down. That means that this equation is going to be mbg, because they point the same direction as mba, minus the tension. All right, so in this problem, what am I looking for in this problem? I am looking for the magnitude of the frictional force, not a coefficient of friction, but I'm actually looking for F in this equation. Let's see, I have the acceleration, I have the mass of A, I have the mass of B, I have the acceleration. It's the same acceleration in both. If the box is accelerating left, the ball's got to be accelerating down the same way, or else the tension would have slack in it, and that's not going to happen. I have G. I don't have T, but what I can do here is I can take the top equation and the middle equation, and I can set them equal to T, and then set them equal to each other, or I can substitute in. There's so many things I can do from here. It's all math, and we can do different things to get the same correct answer as long as we follow the rules of math. So I'm going to rewrite the two equations I'm working with. That's going to be the top one. That'll be m subscript a times a is equal to T minus friction. And the bottom one, which is going to be m subscript b times a, and that's equal to mb g minus t. Let's see, I think what I'm going to do is I'm going to start by the first one, the first equation. I'll number them 1 and 2 just so I can talk about them. So in equation 1, I'm going to isolate for friction. So in equation 1, friction is equal to T minus m subscript a times a. All I did was move friction on the other side and move MAA on the opposite side. So that's number 3. Now what I'm going to do is I'm going to take equation 2 and solve it for T. So equation 2, if I solve it for T, that's going to say that T is equal to the mass of B times G minus the mass of B times A. And I'll call that equation 4, so just so I can talk about it. Now what I'm going to do is I'm going to take the T in equation 3 and replace it with that expression for T in equation 4. That is, I'm going to treat this like it's one number, the m subscript B times G minus m subscript B times A. So that's going to mean that friction is equal to, I'll put it in parentheses just to make it stand out, but it really doesn't need to be in parentheses in this case. Mass of B times G minus the mass of B times A minus the mass of A times A. So I know these masses, I know G, and I know the acceleration. I have everything I need to find friction. Excellent. So now I'll put in my numbers. Friction is equal to, let's see, I'll just throw them right in, although I see some things that can be combined. I mean, nah, I'm not going to do any of that. I'm just going to leave it like this. So the mass of B, which is 6 kilograms, so that's 6 kilograms times 9.80 meters per second squared on the Earth, minus the mass of B, that's going to be 6 kilograms, and this problem tells me the acceleration up here, so that's going to be 2 meters per second, so that's times 2 meters per second squared, minus the mass of A. So let's see, what is the mass of A? 2 kilograms. So 2 kilograms times the acceleration. And it's going to be the same acceleration because everything's got to accelerate together to keep tension in the rope. So there's my 2 for the acceleration. Now when I do the math, I get the fact that the frictional force for this problem is going to be 24.8 newtons.